Let's jump right in. We're going to challenge a very fundamental assumption in the software engineering world today. When we think of senior developers, we usually picture these coding wizards who just sit down and write significantly better, more elegant code than everybody else. But what if I told you the true mark of a senior engineer isn't what they create, but what they destroy? Welcome to this explainer on high-performance back-end architectures. Today, we're unpacking the systemic optimizations, the hidden network taxes, and the brutal production nightmares that shape how senior back-end engineers really think.
This quote right here perfectly captures what we call the code deletion paradox. Your true value as a developer actually skyrockets as you systematically eliminate complexity. Senior engineers know deep down that every single line of code is a massive commitment. It's a liability that can break, it needs constant maintenance, and it just adds to the collective cognitive load of the entire team.
The difference in mindset is just stark. A junior developer joins a project, and they immediately start building, right? They implement new APIs, they add validation layers, and their contribution graph ends up looking like mountain peaks, maybe adding 50,000 lines of code in a single year. But a senior developer? Their graph often looks more like a valley. They might delete 15,000 lines by ripping out unused microservices or consolidating redundant functions. They are ruthlessly stripping away liabilities.
And it all comes down to the 10x rule. Code is read 10 times, modified 3 times, and debugged twice. Our human brains can only hold so much in working memory. Stripping away unused features, premature optimizations, and that classic just-in-case logic isn't just about saving disk space. It is literally the fastest way to accelerate future feature development because you're dramatically reducing the cognitive load for everyone.
Section 1. Escaping the network tax. Let's move from code-level complexity to the brutal reality of distributed system latency.
To really understand the scale of this network tax, just look at this number, 30,000. In a hyperscale environment like Uber's, a single ride-hailing request can traverse 500 discrete services and trigger over 30,000 remote procedure calls. That massive scale introduces a huge combinatorial explosion of failure modes. When you have that many interconnections, latency is absolutely not a static metric. It's a dynamic, compounding beast.
Which brings us to how we actually connect these services. Relying on REST for chatty microservices, where you're blasting a high frequency of small messages, causes major issues. REST over HTTP 1.1 suffers from head-of-line blocking, meaning one delayed response stalls the whole connection. Plus, JSON payloads are just bulky. Senior engineers almost always choose gRPC for high-throughput internal traffic because it uses compact protobuf binary messages and supports HTTP2 multiplexing. It cuts that network tax right down.
But beware the silver bullet. Teams often rush to introduce a service mesh, like Istio, to handle connection balancing. But here's the catch. That heavy Layer 7 proxy overhead adds 1 to 3 milliseconds of latency per hop. Think about that. If your request makes 10 hops, you just lost 30 milliseconds to proxy overhead alone. A senior engineer knows you only introduce this massive operational complexity if your traffic volume absolutely justifies the cost.
Section 2. Database and caching pitfalls. This is where textbook expectations collide with real-world production traffic.
Check out this number, 54x. That is the staggering performance improvement a system can gain simply by fixing the naive N+1 query problem. It's honestly one of the most common silent killers of backend performance out there.
Imagine you need to load 100 users and their posts. An unoptimized system makes one query for the users and then loops through them in memory, making 100 separate queries for the posts. That's 101 round trips taking over 800 milliseconds. But if you optimize that into a single SQL join query, it drops to 15 milliseconds. Looping through in-memory objects to fetch related data will absolutely crush your database connections under high load.
And here is a golden rule straight from the production trenches. Never perform a network call inside a database transaction block, period. When you do this, your database enters an idle in transaction state. It's allocated a worker and locked to connection, but it's just sitting there, completely frozen, waiting for some slow external API to respond. This state is the absolute #1 killer of database performance at scale.
So to protect the database, we use caching. Serving data from memory caches like Memcached or Redis is 10 to 100 times faster than hitting a disk. It offloads the read load so your primary database can actually breathe. But it comes with a major catch: cache staleness. Senior engineers have to implement ruthless time-to-live, or TTL, strategies and efficient serialization so the cache doesn't just end up serving outdated junk indefinitely.
Section 3. Designing for true resilience. Let's shift focus to how architects build systems that anticipate network failures.
In distributed systems, networks drop responses. It's inevitable. The client will retry. And this is exactly where idempotency comes into play. If your operation isn't idempotent, that retry might result in a duplicate credit card charge or a totally corrupted state. Idempotency is a mandatory reliability pattern. It guarantees that no matter how many times an asynchronous fire-and-forget operation is executed, the result remains safely the exact same. But idempotency isn't free, right? Natural idempotency, like an HTTP put, is great because it needs no storage. But for complex workflows, you need explicit keys, like a UUID generated by the client. The trade-off? You have to store those keys in a database to look up duplicates. Hyperscale companies literally store terabytes of 24-hour deduplication data just to safely handle these network retries.
And this leads us right to the CAP theorem, the balancing act between consistency, availability, and partition tolerance. When the network splits, you cannot have both consistency and availability. It's impossible. High-traffic systems like major e-commerce platforms strictly prioritize availability and partition tolerance. They'll gladly accept temporary, eventual consistency like a slightly out-of-date inventory number just to make sure that checkout button stays online.
Section 4. DevOps Production Nightmares. Bringing it all together with real-world outages where the metrics were green, but the system totally failed. Imagine this scenario. Your enterprise users are getting 502 bad gateway errors, but your application logs show a perfectly successful 200 OK. Your CPU is completely flat. What is happening? Well, a junior engineer might just restart the pods. A senior engineer looks at the boundaries. The actual culprit? A bloated JWT payload packed with dozens of user groups hit the hard 64 kilobyte HTTP header limit of the AWS load balancer. The request was completely dropped by the infrastructure before it ever touched Kubernetes.
Here's another nightmare. Your deployment succeeds, the pod is running, the health probes are perfectly green, but 100% of your traffic is getting a 403 forbidden error. Why? Because the code isn't the only thing that matters. This is the silent danger of fragmented configuration management. The API key in the external cloud secret was rotated, but it desperately desynced from the running Kubernetes environment.
To solve this, a senior engineer executes a structured debugging masterclass. Step 1. Inspect the live config directly inside the running pod. Step 2. Verify the actual mounted secret content against the source of truth. Step 3. Audit the deployment pipeline. And Step 4. Identify the root cause. Realizing the CI/CD pipeline deployed the new code but completely ignored the operational context of the external secrets.
So how do we prevent this permanently? Senior DevOps engineers don't just patch the bug, they build guardrails. They add config hash annotations to force a rolling restart whenever an external secret changes. They implement deep health checks where the readiness probe actually validates the external API key, instead of just returning a lazy 200 OK. They use GitOps to deploy the entire operational context, not just the binary.
When it comes to API contracts, breaking clients is a cardinal sin. Enter the expand and contract pattern. If you deploy a change that just renames a JSON field, you will silently break millions of mobile clients out in the wild. Senior engineers never rename a field. They expand by adding a new field. They wait months for the client migration metrics to hit 100%, and only then do they contract by deleting the old field.
And to enforce this, you need strict automated testing policies. We're talking consumer-driven contract testing, where if the backend breaks the Moby team's expected payload, the pipeline fails immediately. We're talking strict API versioning and post-deployment shadowing to catch missing JSON keys before they ever hit production. Your API is a legal contract with the user. You cannot unilaterally change it.
And that brings us full circle. As we've seen through the network taxes, database pitfalls, and architectural guardrails, complexity is the true enemy of reliability. Treat the network as an application in its own right. Ruthlessly reduce cognitive load. So I leave you with this final, provocative thought. Next time you are about to implement a new, clever feature, ask yourself, what can I delete instead?